In this video we're going to discuss something called the rate determining step and then the reaction mechanism and how rates of reaction, how the physical chemist determining rates of reaction and the orders can take part in coming up with the reaction mechanism, how they can help chemists to decide on the mechanism. And that is all by identifying the slowest step in a sequence called the rate determining or rate limiting step. So our slowest step in our mechanism is called our rate determining step. And our rate equation gives us information about this step and all the steps that might happen prior to this step, but it doesn't give us any information about any steps that come after this. The steps that come after this will always be faster than this because this is the slowest step, and our rate equation is not going to tell us anything about them. So our rate equation just tells us about the things that determine the rate, and the rate is determined by the slowest step in a sequence. So you can think of lots of analogies, but if you think of like factory production lines, whatever step is the slowest, maybe it's packing them in the boxes, that would be the rate determining step. If the slowest step in a process, for example in making a sandwich, is buttering the bread, doesn't matter how quickly people put the ham or the cheese inside the bread, you will be slowed down by the rate determining step. So the rate determining step is the slowest step, and the rate equation gives us clues about the rate determining step. So here we go, we've got an example of an equation, and in this example it says A and B are our reactants, and we've discovered the rate equation probably by the initial rates method, and it comes out to be rate equals K times A to the power 1, B to the power 1, i.e. first order with respect to both reactants. Okay, so what does that tell us? That tells us that there's 1 mole of A and 1 mole of B in the steps up to and including the rate determining step. Okay, so normally at A level that usually means that there's 1 mole of A and 1 mole of B in the rate determining step. It's very unlikely that there will be more steps prior to the rate determining step. But we will have an extension example later on that does consider that. So if there's 1 mole of A and 1 mole of B in the rate determining step, and there's 1 mole of A and there's 1 mole of B in the overall equation, then this can be the only step. This can be the only thing that's happening in this reaction. So it's not a multi-step mechanism. The rate equation matches the stoichiometry, the numbers in the rate equation match the overall equation, and so we would say that this is a one-step reaction. So I'm going to pause the video and just write some of that down. So there we go, what have we determined from the information? So because the order with respect to A was a 1 and the order with respect to B was a 1, that tells us there was 1 mole of A and 1 mole of B in the rate determining step. For A level it is usually just in the rate determining step. It technically is in all the steps up to and including the rate determining step, but for A level we're usually considering that as the rate determining step. Now that matches the stoichiometry. Stoichiometry is the big numbers in front of the things in the chemical equation, and since there is 1 of each of those, that means that this is the one and only step. This mechanism just occurs as the equation has been written. A and B just bang into each other and react. There are not multiple steps. Let's have a look at our second example. Now if we look at our second example, we can see that the order with respect to y is 2, but the order with respect to x is 0 because it's not. So order with respect to x is 0 because it's not there, but with y is 2, which tells us that there's 2 moles of y but no x in the rate determining step. That means there must be more than one step because x is still a reactant in this equation. X still needs to occur somewhere. It must just occur in a later, faster step. So we may be asked to give an example of a mechanism for this. And this is the bit that can seem a little bit daunting at first, but it's not too bad. You just need to think it through step by step. So we know that our rate determining step has 2 y's in it. And we know overall that the overall equation is x plus 2y makes z. Okay, So if we were suggesting a mechanism for this reaction, what we might look and say is, well, we know that the rate determining step only has 2y because our rate equation tells us that there's just 2y in it, but that we know overall there needs to be an x. So in a second step, a later, faster step, there must be an x reacting. Now 2y can't go and make z straight away, so because we know there's another step, so 2y makes an intermediate. And that intermediate is the bit that can seem a bit difficult to come up with, but it's not too tricky, we'll just have a go. Now that intermediate is just that, it's an intermediate, so whatever it is, it needs to get used up again. So we put it here and react it with x, and we know that when the intermediate reacts with x, we make z. Now if we were to add these up, we would see that the intermediate would cancel out, and that the overall equation is what's written at the top. We know that this second step is a later, faster step. Anything that comes after the rate determining step is a later, faster step. So we're going to have a go at some more examples. So here we've got an example. We've got 2-chloro-2-methylpropane reacts with aqueous potassium hydroxide according to that equation. And we've been given the rate equation here. And what we can see is that the rate is equal to K, the rate constant, times by the concentration of just the 2-chloro-2-methylpropane, but not the hydroxide ions. So what that tells us is that just the 2-chloro-2-methylpropane is involved in the rate determining step, and that the hydroxide ions are involved not in the rate determining step, but in a later, faster step. So we need to come up with a two-step mechanism. Now this could be a curly arrow mechanism or not. I'm going to do it without the curly arrows just to start off with, and then we could add in the curly arrows from our knowledge of organic chemistry. Mechanisms don't always have to have curly arrows. They do in organic chemistry, but not generally. So we know that the rate determining step just has one, because the order was a 1 up here, one of this halogenoalkane, and then it goes to something. And we need to suggest what that something is. Now we need to use our knowledge of the mechanism of halogenoalkanes to think, well, what could that be? We know in the second step the hydroxide ion has to react. And at the end of it all, we do need to have made the product. So how could that hydroxide have got on there? If we have a little think about it, it seems sensible that it could have come from a negative ion reacting with a positive ion, like that. And then that must be our intermediate, so that's come from here, which could have happened if it had lost the chloride ion. So if we wanted to add in curly arrows, we could break off this bond, and then we could use a lone pair on this hydroxide ion to make the new bond. But the question's not really about curly arrows, it's about identifying steps in a mechanism. This is a later, faster step. So the slower step is the breaking of the bonds. The two ions coming back together is a much faster step. Then we've got a different example here. This one was found to be first order for both 1-chlorobutane and the hydroxide ions. So we know that it's got both CH3, CH2, 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 Cl and the hydroxide ions first order. So this time what we can see is that that matches, there's one of each of these, that matches the stoichiometry of the overall equation, so it all happens at once. This might seem more familiar in terms of the mechanism that you know. So if I was to draw that out like this, and we can put the curly arrows in if we want to later, but we know that both of them are there, and then we've got our product. If we put in our curly arrow, we can do that straight away in one go. Okay, so that's just tying it to something that you've maybe been familiar with. What we're going to do now is have a look at a slightly less familiar example. So it says the rate of reaction between NO and O2 was studied, and the rate equation is rate equals KNO squared. So pause the video and have a think what you think that tells you about the rate determining. So because it's order 2 for NO, 2 moles of NO involved in the rate determining step, no O2 in the rate determining step because it's 0 order. So we need to suggest a possible 2-step mechanism. So our rate determining step we'll do first. We know we've got 2NO and nothing else. So how do I know that there's nothing else? Because the rate equation tells me there's nothing else. Oh, didn't mean to have a double-headed arrow, so I'll just get rid of that end. Okay, so I know there's 2NO. Remember that I know the overall equation, so I can think at the end when I sum it together that I need to end up with 2NO plus O2. This is not part of my answer, which is why I've changed colour, equals 2NO2. So this is the bit where we have to have a little think. We know that there's only 2NO in the rate determining step, so there must be an O2 in the second step, so there must be an intermediate. And you've got to come up with something chemically sensible. There's more than one possible answer here. As long as it's chemically sensible, it's correct. So what might happen to 2NO? Well, maybe it breaks up into nitrogen and oxygen. And as long as you get those formulas right, that would be fine. Maybe we make some of the product. We can make 1NO2. That's some product. What would be left over? Now, if you just count up the atoms, what you'll see is you're left with 1N. Now it needs to be chemically sensible. There is no such thing as just N on its own. It goes round in pairs, so it would have to be half a mole of N2. What we know is we can't change the 2 in front of 2NO because of the rate equation, and that anything we make that is not in the overall equation needs to get used up. So we know that there's an NO2 in the final answer, but there's no half an N2, so we're going to bring that forward as our intermediate and use it up. And so when we have a half an N2 plus an O2, we get another NO2. If we sum these two together, we will get the overall equation. Now that's not the only possible answer, but that is one possible answer. Okay, let's have a look at the next example. So here's an example. It tells us that the rate equation is rate equals K times propanone times concentration of acid. But there's no acid in our overall equation. So what reasons could we give why this reaction must take place in more than one step? And we just need to think about the ways that the rate equation and the overall equation don't match, and be specific. Don't just say they don't match. Think of the ways that they don't match. So there we go. What we can see is that we've got 1 propanone and 1 acid in the rate determining step, but there is no acid in the overall equation. So that's the first way it doesn't match. And then there's an iodine in the overall equation, but it's not in the rate determining step. So what does that tell us? Well, what we can see from that is that we must have the iodine must be taking place in a later, faster step. What about the acid? How can the acid affect the rate but not be in the overall equation? What do you call something that affects the rate of reaction but isn't used up in the overall equation? It's a catalyst, isn't it? It's something that affects the rate without being used up. So then somebody proposed a mechanism. It looked like this. It's quite a strange looking thing, but could it be consistent? Does it work for the overall information you've been given? So if we have a look, we can see that our slower step, which is our rate determining step, does match the rate equation. It has 1 propanone and 1 H+, and that if we were to add these two up, this thing here would cancel out. It's an intermediate, and the acid is regenerated at the end. It's a catalyst, and so we've got propanone plus iodine makes this compound here, and HI, which was our overall equation. So it matches. Let's have a look at our final few examples on this. So in the lower atmosphere, nitrogen monoxide leads to the formation of ozone. Identify the catalyst. So you need to find something that is used and then regenerated. So you want to find something that is used in the slow step or the first step, but then comes back later on and you can see there that the NO comes back later on. So our catalyst is NO, nitrogen monoxide. So can you write an explanation? So it was used in step 1 but regenerated in step 2. And now we've got to deduce the overall equation, so we just need to add up these 3 lines and cancel anything that appears on both sides. So we're going to add them up and cancel anything that appears on both sides. So the NO is going to cancel because there's one on the left and one on the right. The NO2 is going to cancel because there's one on the left and one on the right. The O is going to cancel because there's one on the left and one on the right. So we're left with an O2 and another half an O2, so 1.5 O2s make an O3. That's our overall equation. So here's our final example, and this one sort of talks about that little thing I said would be a bit of an extension. If the slow step, the rate determining step, isn't the first step, then we're going to need to add up those first 2 to find the rate equation. But let's go through it, complete the mechanism by adding step 3. So let's look at our overall equation and see how it matches. So 2NO, they're already there. 2H2, but we've got 1 H2, so we need another H2 on this line. This N2O2 is cancelling out, it's an intermediate that's being used up. And so now I've got all the reactants, but this N2O is not a product. Water is a product, so that's fine, but this N2O isn't, so I need to use that up. I've made 1 water, but I know I'll need to make another water because overall there's 2 waters and there's a nitrogen, and then we can just check the balancing and see does that balance. That looks good to me. Use the mechanisms to deduce the rate equation. So I'm just going to rub out some of this working out up here. Just go back a little bit there. Okay, I'm going to deduce the rate equation. Now remember that that little extension was that the rate equation includes everything up to and including the rate determining step. So what I'm going to do is I'm going to do my explanation first. So the rate equation is going to show me the moles of the reactants up to and including the rate determining step. So if you get an extension question like this, remembering that the rate equation includes everything up to the slow step, so we're going to add up steps 1 and 2. So if we add that up, we've got 2NO and a H2 and an N2O2, that's adding up everything on the left. Then I'm going to add up everything on the right, N2O2 and N2O and H2O. That is adding up all the steps 1 and 2, so all of the steps 1 and 2, everything up to the slow step. And then I'm going to cancel out anything that's on both sides. And remember that a rate equation just tells us about the reactants, so these are our reactants and these are our quantities. So we're going to go rate equals K NO squared times H2. So there we go. Mechanisms from rate equations.